Now let's go ahead and take a list of possible materials, and we're going to use a slightly different list here. I do want to restrict us to the list that you're going to be using for the exam. So we're going to actually use this list, but we're going to answer the same question. It says, given the reactions at the right, and we'll start here. What is the voltaic cell with the largest potential that you could make in the lab with regular chemicals? And what we're going to do is, so we're going to start at the top here, and we're going to try and find the most positive reduction that we can do. And I've gone ahead and included mostly only things that you can find in the lab, although we'll talk in a minute about that. So here we have permanganate ion plus hydrogen ions goes to manganese oxide and some water. So that one is totally possible. So that's going to be the most positive because we're going for the largest potential. And that'll be our reduction, half reaction. And as far as oxidations, it turns out cesium is not stable, so we are not going to be using this one. When I say not stable, I mean in the aqueous phase it reacts with water, so you would never actually have cesium in water. But magnesium is actually a very good metal, and we've used that in the lab before, and or we would have if we were meeting face to face when I record this video. Anyway, so we're going to choose magnesium and manganese and hydrogen as our reactions. This is going to be our oxidation, so we're going to be turning it around to get a positive 2.37 volts. And if this were a homework problem, you would see a list of materials and you would have to pick which reactions you could do with them. But this is just a very general question. Let me see here. So I've got I'm going to write typically my oxidation on top. There we go. And my oxidation half reaction is going to be magnesium. Solid goes to magnesium ions plus 2 electrons. My reduction half reaction is going to take permanganate, which is MnO4 minus, plus 4 hydrogens, plus 3 electrons, goes to manganese oxide solid, plus 2H2O liquid. And these reactions are on here as well, just it's got slightly different ones, but let's see, let's check them off here. So they're on there, but I've limited it so that it would be easier for you on the exam. But it's the same process. All right, so my oxidation is going to be E naught ox equals 2.37 volts. And my E naught reduction, which I sort of ran out of space for there, is 1.68 volts. And now I need my overall reaction. In my overall reaction, I have to cancel out my electrons, so I'm going to have to do the same thing I did before. I'm going to have to multiply this times 3. I'm going to have to multiply my reduction times 2. And cancel out my electrons. And then write everything that's left. There's nothing else that's going to cancel in this, so I'll just write it. And then I'll add up my cell potentials. So this is going to be magnesium solid, is the only one on the top, plus permanganate, times 3. Plus 2 times permanganate, where that's aqueous, plus 2 times 4, which is 8 hydrogen ions, goes to 3 magnesium ions plus 2 manganese oxide, solid, plus 4 H2O liquid. And then our cell potential is straight adding 2.37 plus 1.68. .05 volts. So, and that's that's a large number of volts. Now, next we're going to draw a picture of this. And our picture is going to be, so picture of a voltaic cell. And voltaic cells always look like this. They will have 2 beakers. They will have a salt bridge. With, could be sodium nitrate, could be sodium chloride, just about anything. Or what's this? Just about those 2 are very safe. Sodium sulfate is another one. Anything that is very soluble and doesn't react. And we need 2 electrodes and a light bulb or a voltmeter. I tend to put a light bulb here. And my light bulb has a filament inside, which is called an incandescent bulb. I'll have to learn how to draw an LED, I guess. And then at 4.05 volts, hopefully we'll be able to light up the light bulb. And for me, I always have the electrons going from left to right. That's just a personal choice. And now, so all of that has nothing to do with the reaction that I've just chosen. Now let's personalize it. My oxidation half reaction has magnesium going to magnesium ions. So in order to do that, I need some magnesium solid. And my magnesium solid is going to, on the metal itself, that's why I'm drawing it right here, is going to be splitting into 2 electrons and magnesium 2 plus. And inside my solution I need an electrolyte, so my electrolyte is going to be magnesium chloride. This is what's called my oxidation beaker, or oxidation cell. Now, on the other side, I need to have permanganate ion and hydrogen ion, and they're going to be making manganese oxide. So I've got my 2 ions in solution. Those ions are going to both come up to my electrode, pick up 3 electrons, and make manganese oxide solid. And that manganese oxide solid, so this whole process occurs on this electrode. It makes the manganese oxide, and the manganese oxide will most likely stick to the electrode and coat it. And it's also making some H2Os. Looks like 2. And let's see, this is called the reduction beaker or cell. Now let's see, details that we have not included that we need to. We have not told you what the identity of this electrode is, and we don't need it to be anything in particular. The only stipulation or requirement is that it can't react with anything. Good choices are carbon solid or platinum solid because they essentially react with nothing, especially the carbon, the graphite, if you will. But platinum's a good choice. I don't know what else you could use here, but those are safe choices anyway. So this is a complete picture of a voltaic cell. I guess there's one other thing you could do. You could draw the magnesium ions being made and then going into the salt bridge to maintain charge neutrality. And then you are getting rid of, let's see, you're getting rid of mostly positive charge over here. So we need a negative ion. Let's see, positives coming in here. We're getting rid of positives. So let's draw the sodiums coming in on the other side. So what we're doing there is we're drawing the fact that charge neutrality is maintained. Charge neutrality is maintained, and the way we're doing that is we're showing that as the magnesium ions are produced, building up positive charge here, they are going in, and as positives, more positives than negative are being used up here, this will become negative, so we're showing the sodiums, the positive coming in there. You could also, or in addition, show the chlorides coming in and the manganeses coming in the other side as well. But as long as the idea that you're maintaining charge neutrality is shown in your picture, all is good.